We figured out the logistic regression model and a cost function j of theta that we're going to use to fit the parameters. In this video, we're going to figure out a gradient descent algorithm to minimize that cost function. And by the end of this video, you know how to implement gradient descent to fit your own logistic regression models. This was the cost function that we had written out on in the previous video. So if we want to apply gradient descent to minimize this as a function of theta, as usual, gradient descent would do the following. It would repeatedly update each value, each parameter theta j as theta j minus alpha, the learning rate, minus the partial derivative with respect to theta j of the cost function j of theta. And so similar to when we were working out linear regression, we need to figure out what is the partial derivative with respect to theta j of this cost function. Oh, and of course in a gradient descent, we do this for all values of j equals 0, 1, up to n, right? So it turns out if you take j of theta and plug it in here, and if you remember your, if you know enough calculus to actually carry out this partial derivative after some amounts of algebra, which I'm not going to do, it turns out that if you compute the derivative, you end up with this formula. Times x I j. And the surprising thing about this is that this, looks the same, or it looks cosmetically the same as we had in linear regression. In fact, for linear regression, right, we had defined a different cost function j of theta using the squared cost function, and then after taking derivatives, we actually wound up with exactly the same function. But of course, it doesn't mean the two algorithms are the same. In fact, in linear regression, that h of x, right? In linear regression, we had h of x equals theta transpose x. I'm just sometimes, I'm filling theta there. Whereas for logistic regression, h of x is 1 over 1 plus e to the minus theta transpose x. Okay, so just because the derivative formula looks the same, it doesn't mean the algorithms are the same, because this definition of h of x in this equation is different. And therefore, to get gradient descent for logistic regression, what you do is you take this formula and you plug it inside there, and that's gradient descent. Next, we'll work out something, and in particular, what I want to do is see if we can work out a vectorized implementation of this, similar to what we had for linear regression. And in particular, what we can do is view, instead of updating theta 0, theta 1, and so on up to theta n, right, in a for loop or whatever, we can think of this as a vector of parameters theta, and in the same way, let's see if we can figure out a vectorized implementation. So in fact, I'd like you to try to do that. Concretely, one iteration of gradient descent carries out these updates simultaneously for theta 0, theta 1, theta n, and so on. And so when we want to figure out a vectorized implementation, we want to view theta 0 as this, right, vector of parameters. We want to view theta as a vector of parameters. And similarly, we also view x as a vector of features. So the question is, given this set of equations that we have in the non-vectorized implementation, right, if you were to simultaneously carry out these updates, what we would like to do is come up with a vectorized update where you update the parameter vector theta. So hopefully you got that this first answer is the correct one, and the second and third choices actually don't make sense, as in you can't actually multiply those things, and so you're multiplying things in dimensions that don't make sense. Just to quickly step through the answer, alpha here is our learning rate, so that's a row number. This quantity here, right, that's a row number. That's the difference between the predicted value and the actual observed value, the actual observed value yi. And then this thing here, right, that's a vector, so that's Rn plus 1. And so this thing is a row number times a vector. So that thing that I guess is encompassed by my purple, my magenta brace, or this thing is a vector, is an n+1 dimensional vector. So you sum up these n+1 dimensional vectors and multiply by alpha and 1 over m, and that gives you the update that you want. And another way to verify that this is the correct answer is to look at this vectorized update one component at a time. And you should be able to verify that if you, boy, I'm running out of colors. If you look at this update, right? So this thing that's circled in yellow, this yellow thing is delta, and you should be able to verify that. You should be able to verify that the first element of this delta. Well, let's write something light gray, right? That this thing I've circled, this delta, that the first component of delta is exactly equal to that, and the second component of delta is exactly equal to that, and so on. In case this is unclear, in case the question of why this is the right vectorized implementation is unclear, you can also review the earlier video on vectorized implementations of linear regression as well, and hopefully that will make what just happened on this slide clearer as well. To wrap up, using this, we now have a vectorized implementation of gradient descent to minimize theta as a function of this, and that will give you your hypothesis, which you can then use to make predictions on the probability of y equals 1 given x and parameterized by theta. One last implementational detail, to see if gradient descent is converging, what you can do as usual is plot j of theta as a function of the number of iterations, where j of theta is now this cost function that we had defined for logistic regression. And hopefully if you do that, if number of iterations is on the horizontal axis, if you plot j of theta, if gradient descent is running correctly, then j of theta should be decreasing on every single iteration. And similarly to when we had talked about a similar method for linear regression, looking at this sort of plot can also help you check if gradient descent is converging. So that's it for gradient descent. You should be able to implement this and get logistic regression running on your problems. In the next 2 videos, we'll talk about a different algorithm for minimizing j of theta that can sometimes be even more efficient than gradient descent.